Hello, my name is Professor Elie Hachem. I work at École des Mines de Paris, and my research group is called Computing and Fluid Research Group at CEMEF, one of the research centers of École des Mines based in Sophia Antipolis. So my research group concerned working on real-life problem coming from industry, coming from different area on engineering, and basically we developed numerical methods in order to answer such industrial complex problems. So my research group is composed of different researchers, professors, doctors, and PhD students mainly. We are basically working on three main subjects. For the first one is fluid mechanics, non-Newtonian and Newtonian fluid mechanics. The other subject is high performance computing and artificial intelligence that support this part of application. And the new one, which is related to biofluid mechanics, where we are interested in health and how to combine artificial intelligence and health problems. I'm honored and excited that I have been awarded by an ERC project, European Research Council project, which is a Consolidator call of 2021. And the project is named CURE for controlling unruptured intracranial aneurysm. So basically, the idea of this project is to develop a high-fidelity approach where we combine fluid-sector interaction with artificial intelligence in order to prevent or to compute risk of unruptured aneurysm. So what are intracranial aneurysms? These are ballooning in the blood vessel in the brain. If it ruptures, it causes a life-threatening bleeding. We can count every year 500,000 that die each year from this problem. And these aneurysms are discovered through classical checkups during a MRI scan. And the doctor will decide two main scenarios. First, based on the shape, location, and geometry of this aneurysm and the medical record of the patient, we can decide to have a conservative management where we can follow the patient to monitor the growth of this aneurysm. And the second scenario where we should operate, basically what we do is we insert some devices like coiling or stent. Basically there are small meshes that are inserted into the artery in order to control the flow inside the aneurysm, and that way we can reduce the flow and prevent the rupture. However, there is two main challenges here. First, to compute the risk analysis through numerical method and artificial intelligence. This is a really challenging topic. And the second one, to make a specific treatment for the patient. And this is both challenges that I'm proposing in my project. In this case, we are proposing a novel immersed method in fluid-sector interaction that will study not only the aneurysm itself, but will take into account the surrounding in order to make it evolve based on the blood flow that go inside the aneurysm. And then we will use high-fidelity meshing in order to capture the real small details like the stent inside this region. So the interaction between the blood flow of the stent and the vessel is very important to take into account. And by doing this, we can go and compute hemodynamics coefficient, such as wall shear stresses, that will tell us how much is important to when to treat and how to treat. And this is basically the numerical framework that I'm proposing, what we call high-fidelity numerical simulation, that combines at the same time numerical simulation and artificial intelligence. This framework will be updated and supported by many real patient data, such as MRI scan, such as 4D flow, and by doing different data coming from experimental, real-life application, and numerical simulation, we can construct, using artificial intelligence, a model that will evaluate the risk more precisely to take the decision to treat or to monitor the patient.